Thank you for the warm welcome. Maybe I just take my mask off for now. Thank you for the warm welcome. Thank you, organizer, for inviting me. Such a pleasure to be here. Now I'm based in New Zealand, and in any case, you guys probably don't really know a lot about University of Otago in Dunedin, so I just going to start with that. So Dunedin is pretty much almost the southern part of the world. It's quite cold. In summer, you probably get about 20 degrees Celsius, but which means we also have penguins and sea lions and things like that for you to enjoy. New Zealand have, well, two official languages that you see here, Maori and Sign language. So we don't have English as an official language, but most people speak English. In any case, we located here such a beautiful campus. It's rated one of the most beautiful campus in the world. Beautiful sceneries. We also famous for partying. Students just come from all over the countries, partying all the time. Even with the good sceneries, partying culture, we do good science. We have 3 medical schools, 1 dentistry school. We have a strong focus on the health science. We also have conducted one of the longest longitudinal study ever. We collected 1,000 New Zealanders who were born on that year, about 50 years ago. So we only have one hospital in town, just looking at all the babies who were born in that year. We have 1,000 of them. And up until now, we still be able to collect that data about more than 95% of the people. So this retaining rate had not been found elsewhere in any other studies. We famous also from the intelligent research. This is led by Tim Flint. I'm not sure if we have any psychologists in the room, but you probably heard about Flint effect, where the children often smarter than you, and your parents often smarter than your grandparents. This happens a lot in developing countries. It may be reversed somewhere, but in any case, we have strong focus on longitudinal studies, strong focus on intelligent research. So when when I start working there, I'm trying to join all this effort that people has been built at the psychology department over there. No, cannot go. By the way, if you have time, I recommended you to listen to this TED Talk. It's such a nice contribution to Flynn. He passed away about 2 years ago, unfortunately. Yeah, so now we're back online. So for this talk, I'm just going to focus on 4 things, and I'm going to keep it to be less about academic talk, but more about some of the studies that we have conducted for public speaking. And Sean, Dr. Sripat had has invited me to give another longer talk tomorrow. So if you are really interested in a longer version of this thing, you can come join us at KMUTT. I think 1 p.m. tomorrow. In any case, so I'm going to go over all these 4 things, starting with changes in cognition as a function of age. I know some of the psychologists in the room, psychologists have been really upset about on cognition and cognitive abilities and intelligence for over the past 100 years. And for the current kind of approach that we've been doing is we come up with certain games that you can use iPad to collect. And with these type of games, the nice thing about it is you can use it on people from across the walks of life, from very, very young to very old with the same games. And the game that we've been using a lot is called NIH Toolbox, developed at Northwestern universities. And with all this game, we can looking at different aspects of cognitions. And I'm going to start with the data that we got from the NIH. It's called Human Cognitive Aging. Released about 2 years ago, where we start to see from these older adults, about 35 years old to about 100 years old, we start to see overall cognition to be in a decline, right? The older you are, the worse score you get from this overall cognitive score from NIH Toolbox, right? But not always doom and gloom. Certain part of your cognition is still intact, especially vocabulary and reading. Psychologists call this in crystallized cognitions. You still see a little bit of up, some older adults are actually better than younger people in terms of knowing more vocabularies, in terms of be able to read quickly. But the thing that we call fluid cognitions is really in a decline. Memory, attention, processing speed. We've been hearing about that today, a lot of them already. But with this type of data, you can start to see one pattern, which is individual differences. Not everyone have declined in cognitions, right? There are a lot of individual differences here. Some people are quite good, even though they are very old. Some people are already bad even though they are quite young. So there are individual differences across ages. That is the focus on my studies. How to capture these individual differences with brain imaging. So now we move on to how to predict cognition from brain MRI. We learned a lot about brain MRI in this morning's sessions, and it's good for me. I don't have to explain a lot of things. People already say that. Already explained it. So can we use MRI to predict these individual differences, the changes in human cognitions? Right, it's just basic questions. And earlier last year, there was a big paper out in Nature saying we really, people collect a lot of data, tens of thousands and even 30,000 worth of data, 30,000 people worth of data, and found very, very weak correlations between brain imaging and cognitions. This paper threw neuroscientists in an array. Like, how do we justify our investment? Billions and billions of dollars has been paid to scan people. In UK Biobank, for instance, they scan 30,000 people. They aim at 500,000, and we still get very weak correlations. What's happening? And that is progress of science. So when I coming to this space, I was thinking, well, I'm going to acknowledge that this is a problem, but can we improve it? And one of the ways that we use to improve this thing is through machine learning, and try to use machine learning to capture cognitions at different aspects of images that we got from MRI. As we learned this morning, there's so many types of MRI. You can use what we call structural MRI. It's very similar to clinical MRI that you probably see, where you can try to see the thickness of your cortical, the areas of each of the cortical regions, the volumes of your brain at the subcortical regions, so a little bit below your cortical sheath, or you can looking at the total brain volumes. We learned about resting state this morning. Resting state is when you are asked to just lying down in a scanner for about 8 to 10 minutes. In that time, we have time series of your whole brain from, depending on your scanner, but typically every 2 seconds, we have the data from your whole brain. Now you can looking at time series that changes at different regions. and see if they correspond to other regions. And we can construct this type of correlational metrics and looking at functional connectivities in the brain and see if these functional connectivities are relating to cognitions, individual differences in cognitions. In this data set, this is the younger one, the Human Connectome Project, the classical one, released about more than 10 years ago from WashU. This is one of the nicest data set I've seen so far. They collect 7 tasks, 7 fMRI tasks in the scanner. So you have to play games, emotional games in the scanner. We're looking at activations during different conditions in the emotional tasks, gambling tasks, language tasks, motor tasks, relational tasks, social tasks, and working memory tasks. We have all this data, activation from each of the tasks. I think Sean just mentions about attentions. Working memory is quite similar to attentions, where you have to memorize some stimulus, and now you have to say whether or not that stimulus is the same one that you saw 2 trials ago, right? So you have to encoding it, manipulate it, and updating it, right? And during that period, MRI can collect your data, and I'll be able to looking at the activations during that task. So a lot of various aspects of tasks, a lot of various aspects of cognitions or neuronal activities that we can get from this data set. How good we are? We're pretty good. So it depending on what we're looking at. So this is the performance of our models. Depending on the modalities, there's some differences in how good MRI signal is in predicting cognitions. So in overall, they're doing quite okay. The nice thing about this thing is we can use machine learning. I think Dr. Shaipat just mentioned this morning very briefly, called stacking. We can use stacking method to combine predicted values from each of the models into one model. And that seems to be the best performing models almost all the time. So this is that thing, the stack model, where we have all sorts of MRI signals, combine them together, give you the best predictions. And this is the scatter plot for that. So we explain around 0.57 here. I think now the newest one that we get it over 0.6 and R square about 30. So it's explain around 30% of your cognition is pretty good. And then I think this kind of paint the bright future for MRI, as long as you be able to capture activities from the whole brain, from every region simultaneously, and combining across modalities, you have a better chance of capturing cognition. And this is feature important maps across the 7 tasks that I talk about that Human Connectome give you. So these are these are the features that contribute to the models. And if you are network neuroscientist, you probably recognize it as something called frontoparietal network that seem to be play a large role in predicting cognitions. And we try that. So we explaining them. So we use explainable AI to explain our models. And we quantifying with some kind of commutation tasks that allow us to quantify uncertainty of our feature important map. In any case, if you'd like to read more about it, those are the 2 papers. For the children part, we even throw in DTI. So again, this is diffusion imaging techniques, looking at wide matter integrity. This probably using kind of the old technique might not be the most kind of exciting thing anymore. It just use FA, but we'll be able to get the prediction quite okay. I'd like to see if we can improve it a little bit more with the newer method for improving pre-processing of this imaging modality. But in any case, this talk is mainly about aging, so we're going to focus on the aging one. So beyond young adults and then children, we already start testing. Sorry. We start testing middle age, which is 45 years old. This is the study local to New Zealand. So we got the data when they were before they were born, right? And then tracing up and the MRI data that we got it when they were 45 years old. And then the human chromosome project aging. So now 36 to 100 years old. After we do a lot of exclusions, we got about 500 left. We combine this kind of young and old people. I ignore the children data for now. The brain is quite different. But for this other set, we have a little bit more than 2,000 people from about 20 years old to 100 years old. We try the same techniques. Every single time we do it, stack model always give you among the best predictions correlation around 0.6. So we're quite happy with it. The same technique we use for younger people, for children, be able to apply to the older one, the middle age at 45 years old, and aging at 36 to 100 years old. Right, and this is the overall result. So the overall performance is about 0.5 in Pearson's. And again, this is I need to emphasize this. This is out of sample, meaning we take some data out, about in 20 different data as using a test set. We build a model in a training set and apply to the holdout data, which means it already applicable to a new people. So if you have a new person coming to your scanner at, say, John Hospital, we should already be able to apply our model to this patient, right? We don't need new, like the whole group of people to demonstrate this thing. This is our sample geared toward translational, right? So next is the generalizabilities. It's not enough to be able to predict one person. We should be able to, let's say, build some models and predict other people who get the data from different studies, from different scanner, from even different countries, speaking different language and stuff like that. We're still a little bit in the early stage for this one, but I'm going to show you what we found for now. We have to start somewhere. The most frustrating thing about using big data set, large scale data set from other people, they don't talk to each other. Everyone use kind of different tasks, right? A lot of time, what we have is all these things that have the same structure image, have the same resting set, and we can try to map them together. But different studies using with different tasks, because cognitive psychologists, cognitive neuroscientists really like to test their own data, they like to test their own ideas. Sean probably like to test attentions and ignore others, and other people like to do different things. So it's very hard to find a match in tasks. So with generalizabilities in mind, we can only focusing on structure and resting state, which are the non-task part. As you saw earlier, if you remember the graph that I presented, the top one is mainly tasks. So now you're gonna expect to see a huge drop in performance, but see, what we can do here. So now we just looking at that 3 studies that I told you about, young adult to quite old, 100 years old. So SCP young adult, SCP aging, and Danin study. We use one of them as a training set and the other as a test set, and see how it general to each other. It can be quite busy things, so bear with me for seconds. So diagonal, it tell you how the non-task modalities predict within studies. So this is the performance we got. It's not perfect. Again, performance drop a lot when you take out the tasks. But here is how we use one of them as a training set and apply it to others one. This is all significant, but it's still not the best. But we still be able to demonstrate that different scanner, different way to collect the data, still have generalizable. So I think we sort of cover the generalizability part. We aim to improve it a little bit, especially try to map the tasks across the studies. There are a lot of machine learning techniques that allow us to do that now. Meta learning and things like that, I think, gonna play a role in the future to improve generalizabilities. In any case, the last topic I'd like to touch on is the reliabilities. I'm not sure if you saw these papers, 2 years ago, 3 years now, I think. This is another big paper that came out and throw neuroimaging into array that fMRI are not reliable. Liabilities, I have a very specific definition here. This is test retest reliabilities. So if you get your fMRI on your brain today, then maybe 3 weeks or 4 weeks later, you come to the lab, do it again. How stable this signal is compared to others. So if you are high in high in the first sessions compared to other people, you should also be higher than other people in the second scan, right? And this study, what they show is that they use the Human Cognition Project, use data from the leading study, looking at each of the tasks that Human Cognition Project have, they didn't have, and looking at a lot of region of interest and see how reliable this region actuations is across time. And they compute one statistic called inter-class correlations, or ICC, and the higher the more reliable, right? As you can see, all the tasks have quite low reliabilities, but structure image, the thickness of your corticals, for instance, are quite reliable, right? So this, once this thing got out, people said, scanning the brains to predict behaviors is a daunting task for fMRI. It's not reliable over time. It seems to be Achilles heel of fMRI. Meaning, let's say if you have an X-ray done, right, today, 2 weeks after you do another X-ray, you expect to see the same bone of your shoulder across the 2 times, right? fMRI cannot provide you with that. Doesn't mean that fMRI is useless in translational neuroscience. We may not be able to use it at all, even though we spend a lot of money on this thing, right? Again, I'd like to see if machine learning can help with it. We do the same thing, right? Combine data across modalities from SCP or human cognitive data set. This one is the ICC level. And this is, the best one is always be, those structure image. When you see cortical thickness, if you're high in one, you're probably high in the other, right? But now what I like to focus on is when we combine all the modality together or combine the tasks together, we boost up the reliability into the very, very acceptable, or even the people say excellent level of ICC. So it seemed like my first sessions, I'm also the lowest in the second sessions. You still see some noisiness here, but overall, we should be able to get reliability of the signals with machine learning. What really happening here is that maybe if you could focus on the data from the whole brain, from every area simultaneously, and maybe from any other modality as well to constrain your models, then things start to be reliable. So now things are reliable and predictable. Just like to recap again. We start to see some changes in cognitions as a function of age. Preserved, but some of them are very in a decline. We should be able to predict with some certainty from MRI, and our signals are somewhat generalizable, but very, very reliable. And I'd just like to thank all these beautiful people in my lab. I also have very, very small lab, one PhD student. Well, this year I'm gonna have 2 more, and some research assistants with collaborators mainly from the UK now. I have not talked about these people work yet. Maybe tomorrow. I also link genomes or polygenic score that we got from the whole genome of people to the brain data. Yeah, so if you have time, if you come join us there at KMUTT and all the funding agencies that we have there. Thank you.
Thank you very much, Dr. Narun, for your wonderful talk and very interesting data from overseas. Now is okay. Have you to be our last question because we were not. Yeah, please.
I get to ask first question, and then it's going to be the last. I'm sorry, guys. Talking about generalizability across different scanners and such, but you also have a handful of data across lifespan.
Yeah.
Have you tried to see if there's any pattern that could be generalized across age, if anything? Like I know that it's going to be difficult because different age group would do different tasks, but let's say you focus on something that they all have, like something like see any consistent pattern across age. That's my question.
So that was we demonstrate there. You can see the generalities. These 3 studies are from different age groups.
Oh, I see.
So
Okay.
the generalizability is about 0.2, 0.3.
Then the next question would be, would you be able to also say what is the factor that consistent across age? Because we don't just want to say that it's consistent or generalizable, but we want to also be able to say what is generalized and what is not generalized.
So once we found a model that is generalizable, right? Now we try to explain it, and we developed the methods. It's called In-Explorer. It's developed by my collaborator at the National Institute of Data. We're the first who use it in MRI data. It works pretty much the same way.
Okay, so you're going to pull out the factor that actually consistent across age group. That's interesting because then you can look at the, when they get older, whether they have this problem in MCI or Alzheimer or what's not.
Yeah, one thing that I have not done, I need to make it clear for the aging.
Yeah, right.
Which means people might have cardiovascular problems, but they should not have
brain disorder.
The brain disorders.
Right, then you can test that in clinical population.
Yeah, so now we start to use UK Biobank from 30,000 people across in the UK, and now we're gonna have all sort of interesting things happening there. Yeah, I think it's population based. For me, at least, population-based type of data is the key to understand the variations. We don't want to focus. So now we can be able to looking at the spectrum from the whole population perspective.
Okay, cool. Just one question, right?
Of like dynamical change across like the things that's not linear, like like as you grow up and maybe there's age.
We have to start somewhere. We have not been able to looking at the change in the brain yet. But now, in about 2 years from now, SCP aging will give us the next data set. So they longitudinally trace people, I think, in a span of 3 or 4 years. So now we're going to have the data before and after. Now we might start to see if we can forecast the change. And UK Biobank just released, just got a funding to look at the second scan as well. So all this beautiful data set will help us tracing the changes in the brain. Yeah, so it's quite different from looking at a snapshot of the brain at the cross-sectional part versus the changes dynamically, probably non-linear. That the brain change. Brain always change. Right. Thank you.
Thank you very much. So thank you so much, Dr. Narun Pat.